So let's get started. So this slide was made for people who are not familiar with tensors, so I guess I don't have to spend too much time on it. So very briefly, we will take a very down-to-earth point of view. So for us, a tensor will be a multidimensional array. And for this talk, it's only going to be a three-dimensional array of format m times n times p. And so you all know what a rank 1 tensor is. And then the tensor rank, as we have seen, it's the smallest r, such that you can write down your tensor as a sum of r rank 1 tensors. Okay. So I'm going to present as maybe a main result and an algorithm for computing such decompositions given t, given the entries. And in general, this task gets more difficult as r gets larger. So it's well understood how to do this, especially when r is less than n. But ideally, how large can R be? If you pick a random tensor by counting the number of parameters, you can see that it should be of order n square, and it's also the worst case. It's order n square. But as you will see, we can only go for now up to very much smaller values of R, like linear in R, whereas in the ideally, you would like to go as far as quadratic in n. But we are only linear so far. Okay. So what's known about the complexity of computing tensor decomposition? So this, as was already mentioned, this was shown by Hestad to be NP hard already a long time ago. And in fact, since then, it's been shown to be complete for this so-called existential theory of your field. So you can replace k by whatever field you're working on, like the rational numbers or the real numbers or the complex numbers. It's complete for this existential theory, which means that basically it's as hard as deciding whether an existential formula over k, so it's a first order formula, is true or not, which means it's very hard. And for instance, for k equals q, it's not even known to be decidable, but that's what it is. And since then, there has even been some results on approximation, so it's now known that approximating the tensor rank within a small multiplicative factor is also NP hard. But this is not what I'm going to pursue here. I want to find out the exact value of a rank and to compute a corresponding decomposition. But it's NP hard, so what can we do? Well, you have to, if you want an efficient algorithm, meaning polynomial time, you're going to have to make some special assumptions on your input tensor, and there are various things that you could try. So for instance, you can try average case analysis. So you could pick, in general, so your inputs from some uniform distribution, or in tensor, I think, tensor decomposition, people have worked especially with Gaussian distributions. So that's one way. A more general setting, more difficult, but more general is smoothed analysis. So the idea is that you're going to pick arbitrary vectors in the worst case. So you pick them in the worst case. And then you apply a random perturbation to your vectors. So you could if you apply a Gaussian perturbation, you might end up with, again, a Gaussian distribution like previously, like here, but non-centered. Now it's not going to be a centered distribution. And what I'm going to do today is it's a third option. It's a more algebraic approach based on a genericity assumption. So this means that my algorithm will apply whenever these components they fall outside of hypersurface of bad inputs. Okay, so in particular, it means that all the NP-hard, there are NP-hard instances, they must all fall on this hypersurface of bad inputs. Okay, if you're not exactly on the hypersurface, it's easy. Decomposition is easy. Good. Any questions so far? What's the question?
Do you fix the R?
Yes, the R, yes. Yes, the R, actually, the R will be pretty small. It will be less than, more than n. It will go as high as, so this is like a spoiler, but it will go as high as 4n by 3 in this talk. Okay, so there's also uniqueness in the title. So I mentioned this famous cross-curl uniqueness theorem for comparison. So there's this definition of a cross-curl rank that you may have seen. So when you're given R vectors in n-dimensional space, this is the largest K such that every subset of K vectors are linearly independent. And if you pick your vectors at random, basically the cross-curl rank will be the minimum of R and so of a number of vectors and n the dimension. And yeah, it can never be, of course, larger than R or larger than n. So this is the cross-curl rank. And with this notion, you can then state this cross-curl uniqueness theorem. So here it goes. So you have three sets of vectors. There's the ui's, the vi's, the wi's. And then for each of these sets, you can define a corresponding cross-curl rank, ku, kv, and kw. And now there's this funny condition. If ku plus kv plus kw is larger or equal to 2 times r plus 2, then the rank of T is exactly R. And moreover, this decomposition here, it's the unique decomposition of rank R. Okay, unique decomposition as the sum of R rank 1 tensors. And of course, unique is only, as we have already seen many times in this first 2 days, they're only unique up to scaling. Okay, so that's the uniqueness theorem. Okay, so that's very nice. Unfortunately, there are, for many of the tensors that we care about, such a result does not apply because their decomposition is not unique. For instance, if you take matrix multiplication, as we have seen, I think, this morning, it has symmetries. It has non-trivial symmetries. So, for instance, matrix multiplication satisfies this wonderful identity. So this means basically that if you have an algorithm for multiplying two matrices A and B, you can fix any M and pre-multiply A by M and B by M inverse. And this will give you a new sort of new decomposition, new multiplication algorithm, which yields a new tensor decomposition in the tensor framework. So there's no uniqueness of decomposition unfortunately for matrix multiplication, but throughout the talk, I will only work with tensors that have a unique decomposition. So yeah, unfortunately, none of what I'm going to talk about can apply to tensors like the matrix multiplication tensor. And then, okay, so to go back to uniqueness, so that's a very nice result, this uniqueness theorem. Unfortunately, we do not have an efficient algorithmic version of this. So it's not known, the proof is not super constructive. I mean, you can, people have tried and I guess succeeded partially to have an algorithmic version of this, but it's not, doesn't turn in polynomial time. So there's no known polynomial time algorithm that would actually compute the unique decomposition that is promised by this uniqueness theorem. Okay. So let's try to see how far this uniqueness of decomposition, how far does it apply? So this is again the theorem restated for convenience. So you see that if you have a tensor of size n by n by n, this Ku, Kv, and Kw, they're all bounded by n. So this is going to be applicable as far as 2r plus 2 is equal to 3n at most. So r can be at most of order 3n by 2. Okay. 3n by 2, so that's very far from, the quadratic rank that you get if you pick a random tensor. And actually, if you want to have this 3n by 2 bound, you actually need to have a tensor that's large along all the 3 dimensions. For instance, sorry about that. If you look at the third dimension P here, so if it's small, like for instance, if it's 4, it's going to be applicable only up to I equals n plus 1. So you need to have a big tensor, a tensor that's large in all dimensions, typically a cubic tensor. That's what it is. So as I mentioned, there's no efficient algorithm for this, but there is one special case of this theorem which has actually an efficient algorithm, a nice algorithmic proof and an efficient proof, if you will. So it's the case where you only assume that the Kw is at most 2. So you assume that the Wi's are pairwise independent. So you're going to replace Kw by 2 in this inequality, which simplifies with the 2 that you have here. So what do you get with this? You get that if the Wi's are linearly independent and the Ui's are linearly independent, so pairwise linearly independent, and the Ui's linearly independent, and the Vi's linearly independent, then the rank is R, the decomposition is unique, and as I mentioned, there is an efficient algorithm which is known as the simultaneous diagonalization algorithm. It's also sometimes called the Gen-Rich algorithm. You see that since these vectors have to be linearly independent, this can only apply up to R at most n. Okay. So you have the rank is smaller than the number of variables. So this is the so-called undercomplete setting. So the new result that I'm going to present is a decomposition algorithm for the overcomplete setting where R is larger than N. I will actually use this Gen-rich algorithm as a subroutine. So I will also present what this algorithm looks like and explain a little bit why it works. All right, so now before getting into the more technical part of the talk, so you have here this nice cube, so that's your input tensor. And I am only going to use some linear algebra, okay? So I'm going to view my tensor simply as a set of P matrices. Okay, so T1 is going to be the front slice, and you have T1, T2 up to Tp. This is the back slice, okay? So each slice is an M times N matrix. And then just to remind you of this notation for the commutator, AB minus BA. So the rank is going to be a measure of the lack of commutativity, if you will, of your matrices. So commuting matrices are going to play an important role in this talk. All right, so this is the new result. It is a uniqueness theorem. The statement, it's maybe a bit more complicated than the Pascal theorem, but the point is that there is an efficient algorithm for it. So when these conditions are satisfied, you can actually compute the corresponding decomposition. Let's go through. Oh, this is not working anymore. Can you hear me? Oh, okay, it's on again. All right. Okay, so let's go through these assumptions. First assumption, the WIs are pairwise linearly independent. So this is the same thing as for this so-called Gen-rich algorithm. So I take my P slices. I am going to assume that the first slice is invertible. Okay. So far, so good. Next, since it's invertible, I invert it. I compute T1 inverse, and I multiply T1 inverse by all the other slices. So I get now P minus 1 matrices. And you have these two funny looking conditions that must apply for when you pick any three distinct matrices in this list of P minus 1 matrices. So the commutator, first condition states that the commutator must be of rank at exactly 2 times R minus N. Okay. Or in other words, the image of this linear map must be of dimension 2 times R minus N. So that's one condition. And then this even stranger condition here. If you take the images of these two commutators, you take the sum of these two linear spaces. This is going to be a subspace of dimension 3 times R minus N. Okay, 3 times R minus N. Yeah, so this might look funny at first sight because if you just look at the first condition, you can see that from the first condition you can deduce that the dimension of this sum must be at most 4 times R minus N, 2 plus 2. Okay, but we are not satisfied with this factor 4. The second condition is that the dimension should in fact be exactly 3 times r minus n. Okay. Well, so if all these funny conditions are satisfied, and then the rank is exactly R, and T has a unique decomposition. So it's the same conclusion as the Pascal uniqueness theorem. So these conditions look a bit strange at first, but note that they are actually easy to check when you're given your input tensor. It's not really like this Pascal uniqueness theorem. It's about the U's and the V's and the W's, the conditions. But you don't know these vectors, okay? So if there's even no way of checking that the conditions apply, here you can just, do some simple linear algebra and check that these conditions are satisfied. And moreover, you can find the decomposition.
You mean that the dimension is at most that number, not exactly that one, no?
It has to be exactly, yeah, it must be an equality. Yeah, so, but yeah, it's not obvious. Yeah, it's actually not obvious that there is a single tensor that will satisfy these conditions, right? Because they look very strange at first sight. But in fact, these conditions are generically satisfied. So you pick some value of R. We will see that as long as R is at most actually 4n by 3, you can pick generic vectors ui, vi, wi's, and it turns out that all these conditions will be satisfied. Okay. And so as another remark, so you see this condition that the rank is R. So what does it mean? So we know that the rank is at most R. Okay, so it's an assumption of a theorem. It's an assumption. What this really means is that the rank is not R minus 1 or less, so there's no smaller decomposition. So this statement here is actually, it's a lower bound statement, okay? We have a lower bound on the rank. So actually for the proof of this, we need to build on a lower bound theorem. For this result, actually we build on a lower bound by Strassen, which I will recall. But you need a lower bound for tensor rank. All right. Yeah. So how far can we go? You see, remember, so the second assumption that I had was that the dimension of these vector spaces is exactly 3 times R minus n. So clearly R must be less than 4n by 3. Yeah, so as I mentioned a couple of seconds ago, turns out that these assumptions will all be satisfied for generic choices of these components here. And if I want to compare this quantitatively to the Pascal theorem, so when we have few slices, my theorem is stronger because remember for Pascal we could only go up to r plus 1, to n plus 1, up to r equals n plus 1 for when you have 4 slices. Whereas here we have this 4n by 3, it kicks in directly for p equals 4. So you don't need to have many slices, just 4 slices is enough. So in this way, it is stronger than Pascal, but it's also weaker. It's weaker in another sense. So when you have like a cubic tensor, it's weaker because even for a cubic tensor, you cannot go beyond 4n by 3. Okay, whereas Pascal goes up to 3n by 2. Okay. Any other question on the statement of the theorem? So it's the result of multiplying each slice by the inverse of the first slice. Okay. And actually, we will see later on that an important special case is when this first slice is just the identity matrix. Okay. So in this case, the i's are just the slices. So you can think of them more or less as the slices up to multiplication, but it's a small detail.
Just to be clear, so when you start, the first assumption is that T is already given as this decomposition, right?
No. Well, so there's a uniqueness theorem and there's an algorithm. Okay. So to run the algorithm, you don't need to know the decomposition. It's just that if all these assumptions are satisfied, the algorithm will find the decomposition.
Okay, so if I understand correctly, you have a tensor, and if I just take a random tensor, and if it so happens that these assumptions hold, then this algorithm will give me a unique decomposition.
Yes.
And if they don't hold, this algorithm will just like fail or
Yeah, it might fail. It might fail. Yeah, it might fail. Well, you can, yes, that's a good point. So you, ideally it would be nice to actually get rid of this condition. Maybe it's possible with some further work, but you can just run the algorithm and then check the decomposition that you get at the end. Yeah. Yeah. So what? I mean, so the conditions 2 and 3, you can check them on the input tensor very easily. If you don't know that the first condition is satisfied because you don't know the decomposition, you can just run the algorithm and then check if the output is the correct decomposition. In particular, you can check that the WIs that are produced are linearly independent. Yes. Yes. So if the tensor satisfies all these conditions, the algorithm will work. That's one thing. And the second thing is that these conditions will be satisfied for generic input tensors. So it's not a theorem about the empty set, okay? Which is maybe not obvious from this statement. It's not clear that there is any tensor that actually satisfies these conditions, right? So it's generic in the sense that you fix R and you pick generic UIs, VIs, and WIs. Yes?
But for it to be satisfied for a generic tensor, you probably need a bound on P, like n squared or so.
you need, having large P will not hurt.
At least the R cannot be too big.
No, R, exactly. So R can be at most 4n by 3 due to this condition here. So this thing here, 3 times R minus n, must be less than n. Okay. So this implies that R can be at most 4n by 3. Yes.
Suppose you have T to be written as rank 1 tensors, but it's not up to R, something greater. Can you still apply these? Do you understand my question? If T is like, no, I think I got it.
Okay. Yeah, it's really only up to 4n by 3, and yeah, it's of course an interesting problem how you can you get further to, can you go to higher rank, maybe with different algorithms. But this particular algorithm that I will present, it only goes up to 4n by 3, definitely. All right. Okay. Yes. So yeah. So this is like the more precise statement of the algorithmic result. So as I said, when the hypotheses are satisfied, we can actually run this algorithm to compute the decomposition, and it, it's efficient. So you could ask, what does it mean exactly efficient, and what is the model of computation? So for instance, I will maybe mention briefly overfields at the end of the talk, but you can think, for instance, of your base field as being the field of rational numbers. If you like to work with rational numbers, say the Turing machine. Okay, so the what this means is that the one way of seeing this is that someone picks vectors ui's, vi's, wi's with rational coordinates, okay, and computes the corresponding tensor, and my algorithm will find the ui's, vi's, and wi's that you picked. And this is all going to be running in polynomial time in the usual notion of polynomial time. It will be polynomial time in the bit size of the tensor. Okay. So in particular, a consequence of this, a funny consequence is that these ui's, vi's, and wi's they must be polynomially bounded in the size of t, which is not a priori obvious. So if I go back to the statement here, okay. So what I'm saying here is, if you're given t, then the bit size of the ui's, vi's, and wi's cannot blow up. Okay, it cannot be exponentially bigger than the bit size of t, which is not a priori obvious. I mean, usually when you solve a system of polynomial equations, the size of a solution may be much larger than the size of the input system. Okay, but so here it's not the case, at least when the assumptions of the theorem are satisfied. Yes. Under these assumptions. So yeah, so I don't think that anybody has worked out the details, but I would not be surprised that it's possible to cook. It's probably possible to cook some bad examples where these conditions do not apply and where the bit size of the output is exponential. Okay, because using this fact that this tensor decomposition is complete for this existential theory of K. It's been done already for several ETH complete problem. You can cook examples where other examples of geometric problems where the bit size of the solutions blows up. Okay, but here it doesn't blow up. Okay. All right, so yeah, so this is actually the first polynomial time algorithm for overcomplete decomposition of generic tensors. Again, overcomplete means that you can have a rank that's bigger than the number of variables, than the sizes of your cubes here. So just to mention some prior work, there is this paper where they can go up to n plus any constant k, and they can do symmetric tensor decomposition with a running time that is unfortunately exponential in k. Okay, so it's going to be quite slow if k is not super small. And then there is this very nice result by Johnston, Lovitz, and Vijaya Raghavan, which can go actually up to quadratic rank, but there's a catch. So you need one of the. So you need to have a lot of slices. So one of the 3 dimensions of your tensors must be very large, but just one. Okay. All right, but say for cubic tensors, there definitely was not anything known really efficient above r equals n. But since then, there's been another algorithm of the same kind. So these people, Kotari, Moitra, and Wine, they are going to present at the upcoming Fox conference an algorithm that actually goes up to a higher rank than my algorithm, so they can go almost up to, oops, what is this? They can go almost up to rank 2n, okay? Whereas I can only do 4n by 3. All right. Yes.
Do you have the complexity in terms of n bound
For
n and p and the edge
for my algorithm, it's polynomial. So you want to have an exponent? It hasn't been worked out really. So, one issue is, if you wanted to do this, I might mention this at the end, but it's not even obvious that that this is the model that you would like to work with. So, as another option, you might want to only assume that your inputs are, say, vectors in Rn or Cn, and to compute some approximate decomposition. So yeah, so it's not clear what model would be the best for this kind of analysis. But anyway, yeah, there's no precise analysis so far in any model. I guess you could, in principle, from my algorithm, you could extract some bound, yeah, I guess it's only interesting to work out maybe a precise exponent if you can really have an exponent that's not too big. But I'll mention something about this at the end. All right, so as I said, the statement, as part of the uniqueness theorem, we have a statement that the rank is R. So as I mentioned, this is actually a lower bound statement. And we need to start from an existing lower bound. In our case, it's this lower bound due to Strassen. So this is the statement of his result. So Strassen proved that if you have tensor of format n by 3, so 3 slices, if the first slice is invertible, then you have this funny inequality. The rank of T is bigger than F plus 1/2 of the rank of this matrix here. And actually, you know, this rank here, if you multiply everything by T1 inverse from the left, you can see it's actually the rank of a commutator. Okay, this is the rank of a commutator. And in fact, one of the assumptions of my uniqueness theorem was that, if you remember, so it's assumption 3.1, it's that this R is equal to this thing here. Okay? So if I go back to this statement, you see that the rank of a commutator is 2 times R minus n, so which really means that you have an equality in this inequality here. Okay, so I can try to maybe explain a little bit, but I see that I'm going to maybe run out of time. But I can try to explain some of the ideas behind the proof of this lower bound, because we are actually going to build on this method. So Strassen had discovered that there's a connection between tensor rank and commuting matrices. And more precisely with commuting extensions. So what is a commuting extension? So let's start from two matrices, A1, A2. They might not commute. But now what you want to do is that you want to make them commute, so to speak, by adding new columns and new rows, okay? So now the AIs, you put them in the top left corner of this bigger matrices ZI, and you want the ZIs to commute. And basically the question is, how large must this matrix be? How large must this R be so that these matrices ZI commute, okay? So, you know, I'm using this notation R, same notation as for the tensor rank, because it actually turns out to be the same thing as the tensor rank. You see, so it's not too hard to see that the size of these big matrices ZI must be at least n plus 1/2 of the rank of this commutator. It's a two-line calculation, but I'm going to skip it. So you just write down the product Z1 times Z2 and then 2 times Z1, and you write down the equality that you must have between the top left blocks of these two products, and you get this. And of course, you see that, so you have here this measure of the non-commutativity of A1 and A2. So, you know, it's not so surprising maybe that if these matrices are very far away from commuting, then you need to have many rows and many columns. Okay. So this inequality here is not difficult. The thing that's maybe not so clear is, why is there any connection between commuting matrices and tensor rank? And so I thought I'll try to explain this. Not actually, I'm not going to go through the actual proof of the Strassen lower bound, but I will try to explain a little bit this connection on the example of the so-called Gen-Rich algorithm, which I mentioned at the beginning. So this is, this algorithm I mentioned at the beginning, which actually computes efficiently a decomposition in the undercomplete case. Okay. So you have these 5 simple steps, and I'm going to go through the 5 steps. And in general, it applies for any rank r less than n, but I'm just going to apply it, to need it here when r is equal to n, okay? So first step is to compute 2 random linear combinations of the slices. So you get one matrix TA, another matrix TB. Then what you're going to do is that you diagonalize TA times TB inverse, okay? And then it turns out actually that, well, first this matrix is going to be diagonalizable under some reasonable assumptions, and moreover, the eigenvectors are going to be the UIs that occur in this decomposition, okay? So you recover the UIs, and by diagonalizing a matrix of the slightly, well, of a similar type, you can also get the VIs, okay? So you get the VIs and the UIs, but you only get them as sets. So you have a set of UIs, a set of VIs, and now you would like to know which UI goes with which VJ, okay? So you need to have the right order on your sets. And it turns out that you can find this order by looking at the eigenvalues, okay? So it turns out that the eigenvalues are reciprocal. So lambda I times mu I is 1. So in this way, you can find the right order. So you have found the UIs and VIs. And then to find the WIs, this equality here, once the UIs and the VIs are fixed, it's a linear system with the WIs as unknown. So you solve the linear system, and you get the WIs. Okay. So this is the simultaneous diagonalization algorithm. So why does it work? And what's the connection with commuting matrices? Okay, yeah. So if you have a generic tensor of rank n, it's guaranteed to work, and everything follows from this super useful equality. It's very simple, but it's very basic and useful properties of tensor decompositions. So when you're given a tensor T, a tensor decomposition like this, then it's of course useful to know how the slices can be written as a function of these vectors UIs, VIs, and WIs. And actually, you can write them as a product of 3 matrices. Okay, so the UIs are going to be the column vectors of U. And likewise, you take the VIs, and they will give you the column vectors of V, of this third matrix. And then in the middle, you have this diagonal matrix dk, And in dk, you put the kf entries of all your W vectors, okay? Kf entry of W1, then kf entry of W2, and so on. Okay, so it's a diagonal matrix. Okay, and so we saw in the algorithm that we compute tk times t1 inverse. So if you apply this formula here, you do this simple computation, and you can see that yes, this matrix is diagonalizable, and indeed the U's are the eigenvectors. Okay, so this is what I promised on the previous slide, right? That the UIs are the eigenvectors. Okay. So in particular, all these matrices are simultaneously diagonalizable, so hence the name of the algorithm. And in particular, they must commute, okay? So these matrices must commute, so this is the connection with commuting matrices. And moreover, there's this useful case where the first slice is just the identity matrix. So in this case, the condition is simply that the slices themselves should commute. Okay. Any question on this? Yeah, so that's the Greenwich algorithm. And then, so the idea is to build on this to obtain an overcomplete algorithm. So the basic idea is this. We would like to run the previous Greenwich algorithm on our tensor, but R is bigger than n, and we can only run it for R equals to n. So the idea is to increase the size of a tensor, okay? So we have this input tensor of size n by p, and we are going to replace it by a new tensor of size r by p. And now on this tensor, we have a chance of running the previous Greenwich algorithm up to rank r, all right? Since now r is the dimension of these matrices, okay? And moreover, if we can make sure that the first slice of T prime is the identity matrix, as I mentioned, the slices of this tensor T prime should commute. So this observation will help us actually construct T prime. So how do you construct T prime? Well, if you assume that the first slice of your input tensor is also the identity matrix, to construct the bigger tensor, you just need to find a commuting extension, okay? You need to find a commuting extension of these matrices. And actually there is, so I'm not going to be able to go into the details of this, but there is in a companion paper, I have an algorithm for actually commuting extensions. So once you have done this, you can decompose the bigger tensor T prime using this Greenwich algorithm. And then from the decomposition of T prime, you get a decomposition of T. All right. So that's the idea. And the actual algorithm is here. So yeah, there are some minor assumptions here, technical assumptions that can be removed, but I will just look at this simpler case here. So there are just 4 steps. So first step is to essentially multiply everything, all the slices by T1 inverse to make sure that the first slice is the identity. Then you compute a commuting extension for these P minus 1 matrices. Okay. So now you have a bigger tensor T prime with the identity matrix as its first slice. And on this tensor, you can run now the generate algorithm. Okay. So you will get a decomposition like this. So it turns out that the WIs that you get are actually the correct WIs. So here you do not need to change anything. But these components here, UI prime and VI prime, you need to change them a little bit. So actually, you see these vectors UI prime and VI prime, they are of length R, but you only want a vector of length n. So what do? Well, essentially, you just drop the additional components. Oops, I'm sorry. So you just, for the VIs, you just literally drop the additional components. You just take the first n components. And to get UI, you need to do a slightly more complicated computation, but yeah, it's not that complicated. You just multiply by some matrix. And so this is basically to undo the effect of a multiplication by T1 inverse that we did here. So in fact, one can see that when you multiply all the slices of a tensor by some fixed matrix, for instance by T1 inverse, the effect that this has on the decomposition is just to change the UIs, okay? So this just changes the UIs, so you need to undo this thing here at the end. Okay, so that's this is the whole algorithm. And I'm running out of time. Yeah, so you might wonder, why we had all these funny assumptions on the rank of the commutators and the dimension of the sum of the images and so on. So the reason for this is that this is actually the conditions that you need to compute the computing extensions. So there is also a uniqueness theorem for commuting extensions. So if these conditions apply, the commuting extension is guaranteed to be essentially unique. And there is an algorithm to find it. Maybe I can just explain what it means that the commuting extension is essentially unique. So, strictly speaking, the commuting extensions were never unique, really, because given any invertible matrix M of size R minus n, from a commuting extension, you can find a new commuting expansion like this, okay? Essentially by a similarity transformation. All right. So there's not really any uniqueness, but if these are the only commuting extensions of size R, we say that the commuting extension is essentially unique. And yeah, I'm a bit, I guess, almost out of time. So I can maybe finish by offering some thoughts on what we can do to go beyond 4n by 3. That's the highest rank that we could deal with. So this Strassen lower bound that we started from works up to 3n by 2. So there is still some room for a little bit of progress using this method. Okay. So this might take us to 3n by 2. Then there's this newer result by Koiran, Moitra, and Wine. So they also build on a tensor rank lower bound, but instead of Strassen's result, they use the so-called Kosul-Young flattenings by Lenzberg and Ottaviani. But you could ask, so this only goes to almost 2n. So what if you wanted to go to rank 2n and maybe beyond? Well, the main roadblock is you would need a new lower bound, a lower bound that applies beyond 2n. And for instance, if you want to try this method of commuting extensions, there is a barrier of some kind that applies starting at r equals 2n, and which is that there are commuting extensions that are not diagonalizable. So this was pointed out to me by Gero and Zuidam. So you see, if you take any matrices AI here, you can always build this commuting extension of size 2n, and clearly, these matrices commute and they're all nilpotent. And of course, they are not diagonalizable. And so you see, you can build more commuting extensions using this action of a linear group, as we saw. But when preparing this talk, I realized that actually this commuting extension is not essentially unique, so you have a little bit more. And I'll stop here, I think. So it turns out you can also construct some commuting extensions that are not nilpotent. So you can check that these matrices also commute, and clearly they are commuting extensions of the AIs. So anyway, I think if you want to make progress using this method of commuting extensions and go beyond 2n, maybe we need to better also take into account these non-diagonalizable extensions. And I have couple of slides on final remarks, but I guess I'm out of time, so I'll stop here.
Is there a connection between these two approaches?
I would need to read more carefully Bernard's paper, but maybe Bernard has some ideas. I don't know.
Yes, there are some relations.
Oh, okay. Yeah, but we need to discuss it.
Theorem applies for this multilinear tensor. You have extension of rank R, and you have commuting matrices.
Also, you also have commuting matrices in your.
And for symmetric.
For symmetric.
Tensors, you look at extensions, but they are related to Hanken.
Okay.
Very connected. Other questions?
I have a question. So, about this uniqueness part. So imagine that I give you R equal to, let's say, 100 n.
Mm-hmm.
Okay? And I take my U, V, and W at random. So, am I guaranteed that in this case this decomposition is unique?
No. The uniqueness result only applies to 4n by 3.
Okay, so this uniqueness is for 4n by 3. So even if I told you that I took this UVW at random, you cannot
I'm
say
sorry.
that.
Okay. Yeah. You're asking whether the decomposition is unique You're not asking for a condition that you can check which
Yeah.
guarantees.
Yeah, exactly.
Yes, yeah. I think this is going to be true. I think yes.
Okay.
But the issue is that we don't have an easily checkable condition that will
That will give us
yeah.
this. Yes. Okay. Yeah, that is my question. Thank you.
So the uniqueness theorem, you have okay. In the uniqueness theorem, you have this. In the uniqueness theorem, you have these assumptions with the commutators, but you said that they're not really restrictive because generic tensors actually like
Yes.
I don't know. I found it a bit surprising. Not that I know much about it. But I was wondering if you could expand a bit.
Yeah, you mean explain where this
The dimension of the image of the commutator.
yeah, okay, yes, yeah, I can try to, maybe explain this a little bit. If you give me a little bit of time for this, let's see. Yeah. Like, okay, so for instance, this condition, so I don't want to take the time of the next speaker either, but can I just answer this question, or is it, am I?
Yes.
Okay, so
Maybe.
okay, yeah, very quickly. Yeah, so I can maybe, just to explain the simplest condition. So you want these matrices to commute, okay? So let's just see what happens when you compute the product. So I'm not going to compute the whole product. We don't have time for this. But so you have, let's just look at the entry here, the top left entry. So, you get A1, A2 plus B1, C2. Okay. And if this matrix is commute, this should be the same thing as when you switch the indices 1 and 2. So this is A2, A1 plus B2, C1. Okay, so this means that the commutator of A1 and A2 should be equal to B2, C1 minus B1, C2. Okay. But here you have like R minus N columns, right? This is N columns, R minus N columns. So the rank the rank of these two matrices is at most R minus N. So clearly the rank is at most 2 times R minus N. Okay. So in the theorem, we assume that this inequality is actually an equality, meaning that the corresponding spaces are in direct sum.
Okay, thank you. So we thank Pascal. The next talk is